Now we get to talk about one of my favorite subjects, and that is synthesis. We're going to kind of narrow it down to aromatic synthesis, and of course there are a couple of reactions that might make our lives a little bit easier that I'm just kind of not ready to present yet. So we'll kind of do a some holds barred type of session on aromatic synthesis here. So probably the best way is just to kind of I'll model to you exactly how I approach some of these problems and some of the thought processes that kind of go into them. So the first thing we need is a synthetic target, and we'll start, semi-simple here. And one of the first things I really like to do is I like to get it out of my head and just onto the piece of paper, or in this case, the whiteboard. And by actually doing this, quite often you'll find that even if you can't kind of figure out a process that kind of linearly goes from the benzene starting material all the way to product, it does help you to think about it. And so I'll just kind of like demonstrate that as I write here. So obviously the first types of things we need to think about are how we can actually introduce these different groups, right? And so just without thinking too much about potential problems or order of operation kind of things, I'm going to work backwards. And so I'll use these kind of special arrows, which are called retrosynthetic arrows, that are really no different than a normal arrow going the opposite direction. And, let's say, I want to put a BR on a ring here. And, well, I know a reaction that can put a BR on the ring, right? And so let's just kind of imagine that as I'm thinking about this, I might say start with this and say, well, how do I put a bromine on something like that? Well, I know that I can use Br2 and FeBr3. Are there other ways that I could put a bromine on the ring? Yeah, I guess so. We'll work backwards to maybe this, right, through some sort of diazonium salt. And oops, I'm gaining carbons as I go here. That's no good. And so like a copper 1 salt through a Sandmeyer reaction will get me there. And of course, there's probably a couple other ways I could do that. But I kind of look at this and I say, well, is this going to be a really good ultimate step? And I look at this and I say, well, oh man, there is a problem with that group right there, right? That's an ortho paradirector, and I want to put a Br2 onto a meta position, right? And so I already kind of recognize, well, that might be part of the reaction somewhere, but it's not, it's not speaking to me right now. But what I'm not going to do is I'm not going to erase that thing, right? I'm going to leave it there, and just so that I can refer back to it later. In terms of this thing, right? Well, I know that I can put the precursor to this, which is an NH2 in there. And I think, well, is there any really easy reaction to get that thing in there? Well, we talked about the nucleophilic aromatic substitution, so maybe there was a halogen there to begin with, but that's kind of silly because we started with a halogen. And so, you can kind of see the way that you just kind of end up on these what look like just kind of pathways that are just kind of going everywhere. But I really think this is an important step to think about, just kind of throwing a bunch of stuff on the page and hopefully making some sense out of it eventually. So let's kind of go back here, and let's say we got kind of stumped and we're like, I'm not sure exactly what's going on here. So let's work on the other group here. Well, just kind of not thinking too hard about it. I know there are Friedel-Crafts reactions that'll put that sucker on. And let's say that I maybe start with this. And let's say I treat it with, let's say, aluminum chloride and my 3-carbon piece. And I say, well, I got some other problems going on there. I've got a problem with, well, first of all, rearrangement, right? This is a Friedel-Crafts alkylation, which would mean that I'd very likely end up with this thing rearranging to the isopropyl. So automatically, I'm just going to say, oh, wait, let's not think about that. Let's start with this, right? And I know that that is kind of the step before must have been some sort of Friedel-Crafts acylation. Right? And then I say, okay, well, I know how to put that piece on. Of course, I'm thinking in the back of my head here, I'm like, yeah, I don't really like the order of things here because that's an ortho-para director and I'm trying to direct in a meta position. So that's maybe not great, but it might give me some insight somewhere else. What about this finishing step? Oh, okay, that's somewhere I could use either Clementine Reduction or Kishner Reduction. Let's just use Clementine because it's fun. And so, oh, actually, Clementine might actually be the zinc-mercury couple. I can't remember, but anyway, some sort of transition metal here in HCl is going to end up with a reduction there. And so I'm kind of looking at all these pieces and it doesn't look great, but I definitely have, if nothing else, a bunch of partial credit, right? And one of the hardest classes I ever took was literally called Chem 666, right? The sign of the beast. You know you're not doing things right when you're taking classes that have the sign of the beast for their course number. But it was advanced organic synthesis. And one of the kind of the watershed moments I had where I was like, you know what, Sean, you're not going to ever figure out these problems. They're just too hard. So I'm just going to go for partial credit, right? And for some weird reason, that was enough to kind of like free me to like just throw a bunch of stuff on the board. And like, some people thought it was kind of defeatist, but really it was just kind of a really freeing thing for me. And so I would literally just approach problems like I'm going to get as much partial credit as I can get. And the weird part is that usually I'd kind of be able to put together my hodgepodge of partial credit into like an actually real good answer. So we're going to kind of do the same thing here, right? I'm just going maximal partial credit. And I'm starting to think, well, I kind of had a problem right back here, right? I had that same problem with directionality down here, or directing ability, as I kind of had up here, right? Well, is there any way that I could kind of put all these different pieces together? Now that I'm looking at this, I'm thinking, wait, what if this thing had actually started as the acylation part here, right? Right, and I won't write down the reagents because they're already written over there. Well, it turns out that I could, if I started as this, right, I could take this thing and I could introduce, and I know this is getting crazy looking, but this is what your syntheses often end up looking like. Right? I could introduce a Br2 group here, right? Because that's a meta director. And then I could take this thing all the way through with my reducing conditions, which I've already written down, right? And so even though this thing looks like a horrible mess, this is what I'm looking at for your synthetic reactions here. I really want to see like the way that you're thinking. And once you kind of have all those different note cards that you're kind of flipping through, a lot of times you'll find yourself kind of to a path. And of course, if I was going to, answer this thing, officially on an exam, yeah, I would include all this, but then I'd show like the nice, clean synthesis, kind of like we've seen before. So let me show that on the next video slide here. Okay, so putting all those pieces together, there's kind of what I would write on the exam, I guess. I always really like doing proofs in like math class and just ending it with QED. I don't remember what that stands for, but it feels really good. And keep in mind, right, like there are billions of different ways of doing all of these synthetic, maybe not billions, but many different ways of doing these synthetic protocols. And as we learn more reactions and kind of more kind of stepwise looks at these things, you'll definitely become more efficient, right? But there's no real good way, and one of the things I love about organic synthesis is the only way you really get good at it is just kind of keep practicing, and especially with a little bit of guidance from somebody that might have a little bit more experience than you. It really is an elegant kind of approach to science, and something that a lot of people really like, and I was also one of them. I will be honest, I was never a great synthetic organic chemist, especially not in lab, but the one thing that I wasn't afraid to do is to just try some crap. And I was so used to not coming up with solutions that that whole like linear way of thinking, it was very satisfying to me to have my like nonlinear brain kind of be able to be employed here and kind of divergent thinking. Okay, so let's try at least one more. I'll show you a couple of, other ins and outs involving amines maybe. Okay, so here's one I just kind of made up, and hopefully I'll even be able to come up with the answer here. So let's just kind of freeform. We'll think about different ways of putting a methyl group on an aromatic ring. I should mention the Grignard reaction, that is one of the really, really important reactions we haven't talked about yet, is technically something I haven't talked about yet, so I'm not going to use that here, even though it probably would be the best thing to do. So how might I have put that CH3 group on the ring? Well, we're going to think Friedel-Crafts acylation, perhaps. So we'll just put FC right here. And I do that same kind of thing and think, well, maybe that's not the best order of things. I might use a Friedel-Crafts acylation in there somewhere, but those are not going to direct very well. So maybe instead of doing that, I could imagine that maybe this was an aldehyde, and I'm just kind of like throwing stuff down here. Okay, so I've got a couple of different possibilities. That could have been some sort of reduction of an aldehyde. And of course, Gattermann-Koch reaction could have gotten to there. Let's see. What else could we have done? Well, so we've kind of thought about that a little bit. Let's go down and imagine, well, how might we have introduced these nitrile groups? Well, conveniently, there's only one real reaction that we've talked about that introduces nitrile groups, and that is the Sandmeyer reaction. So let's pretend that we maybe did a Sandmeyer reaction that would have required an equivalent of this, followed by some sort of copper 1 salt to introduce that nitrile. What did that thing start as? Well, that could have started as the aniline. And of course, that thing could have started as an aniline as well. And I remember the reagents that got me here were HNO2, essentially, or NaNO2 with some acid, other things. Oh, well, I guess this could have ultimately come from some sort of reduction of a nitro group. And so what you can kind of see is, I'm really trying to beat you over the head with it here, is that I'm not really, I'm not writing it down because there's some problem with directing ability. I'm just really just trying to use it as a way of me kind of just verbally and kind of mentally putting like note card diarrhea over the page, hoping that at some point something will stick. Sticky diarrhea. Good job, Sean. Developing the theme here, let's go this direction, and we'll think backwards. Maybe it wasn't a reduction that got us here. Maybe instead it was some sort of nucleophilic aromatic substitution, where this thing was some sort of halogen. And that would have taken that, and I'm looking at this and saying, well, it's probably, slightly activated towards nucleophilic aromatic substitution, but it's not ideal because this group is meta, and really what I want is an electron withdrawing group, ortho or para. So maybe I'd be thinking, well, should I bother trying to do this? And so all of this is going to kind of come together, hopefully into some sort of synthesis here. So let's see if I can delineate kind of a path through the madness here. Okay, so here's a potential pathway, right? And by all means, I'm not going to throw something this complicated at you, especially on some sort of celebration of knowledge, right? And honestly, like even this semi-solution, like it has parts that like don't make me feel great, but at least all the reactions I suggested have their basis in some sort of reality, right? So let's kind of highlight a couple of parts that I'm a little nervous about and some reasons for the madness that you see here. Well, first of all, I know introduction of a halogen group is going to open me up for a bunch of different nucleophilic aromatic substitution chemistry. Because this wasn't activated, I knew that it was going to proceed by some sort of benzyne mechanism, which means that you get this mixture of products if I had any other group on here, right? And so I wanted to kind of get that out of the way so that it didn't matter because there's nothing else on the ring for me to put my amine group in there. Then I took that amine group and I turned it into the diazonium salt. I did my Sandmeyer reaction. I pretty much repeated that whole protocol, but I'm a little concerned about this sequence of steps because I am kind of imagining that one nucleophilic aromatic substitution activator, right? That would be a deactivator in electrophilic, but it's an activator in nucleophilic. It's not as activating as it could otherwise be because the whole resonance stabilization, right? It's on the meta position, but in this particular case, I couldn't come up with a real easy way to get around that without employing, secret coupling reactions and other reactions we haven't talked about. So anyway, I just kind of threw a bunch of stuff down, and I'm hoping that that's enough to put the amine group on that particular position. We go through that same protocol of Sandmeyer. I, at that point, have 2 nitriles on there. Pretty deactivated ring. So chances are this particular step, I'd have to beat on it and wait for a long time. So I'm not feeling great about that. But at least both of those groups are going to direct me meta, right? And so this is that Gatterman-Koch reaction. And then finally, I've got this step to convert that sucker into an alkyl group. This is the Wolff-Kishner reduction we've seen before. The reason I chose that as opposed to the Clementine is because once we get to the nitrile chemistry, turns out that if you beat on these guys too hard with acid, you can actually turn those into either amines or sometimes into amides and things like that. So I didn't really want to do that. So instead I went with the basic conditions. And of course, like all of this crap, right? This is it's not something I'm expecting you to come up with like tomorrow, right? This is all kind of stuff that will develop throughout the day. And quite honestly, you're so smart, you could probably come up with a much better synthesis. And I will say that like this is not the synthetic protocol that I would follow only because some of those like coupling reactions are so powerful, right? So like the idea of having a chlorine group in here, you can pretty much couple that thing very quickly with any kind of really appropriate organometallic reagent. It's just that, I didn't want to show you that. And then of course, like that group, I would most likely introduce probably back at this step. I'd turn this thing into a Grignard reaction, right? And I'd have that Grignard attach some sort of carbon dioxide or something like that, which I would then reduce. But, like that's kind of for later. So hopefully this kind of just shows you a little bit of the way to think about these reactions. And hopefully the homework will help you do that as well.